Today we will continue the discussion to energy and power. We'll understand what power is, what energy is, we'll see their definition and formula. We will learn about the units of both of them, and then we will see a simple example to understand the whole concept better. Let us get started with today's lecture. Power is defined as the rate of doing work. Power is the rate of doing work. Therefore, mathematically, power, which is also represented as P, is work done per unit time. So work by time. From the definition we can see that the power will depend on how much work is done and within what time that amount of work is done. So the same amount of work done over a larger period of time will have less power requirement than doing the same amount of work in a shorter period of time. Power is a scalar quantity. Power is a scalar quantity. This means that power does not have a direction. It is not a vector. It just has a magnitude. In fact, in my previous lecture, I missed out on saying that work is also a scalar quantity. Work is a scalar quantity too. Therefore, work has no direction. Work is a scalar quantity, so is power. Now, we know the basic definition of power is work per unit time. From this, we can find an extended definition of power too. What do I mean by that? I mean that work is defined as force into displacement in the direction of the force. So if the displacement is in the direction of the force, then we can write is power as Fd divided by T, and this can be expressed as force into the distance moved in the direction of force by time, and this we can say velocity. This is the velocity. So ultimately power can be said to be force into velocity, and if the direction of force and velocity is same, then velocity and speed will be same, as they are speed is the magnitude of velocity. So power can be alternatively defined as force times velocity, or force times the average speed. So power can also be written as power is force times average speed, given that force and the displacement is in same direction, F and D in same direction. So this is an extended definition. We can directly use this relation in numericals. We can also go through the work by time method. Now that we know what power is, what the definition is, what it means, let us see the units of power. The SI unit of power is watt. W-A-T-T. It's also represented by a W. capital W. Now what is a watt? A watt is the amount of power spent. Amount of power spent when work of 1 joule is done in 1 second. So the SI unit of power is watt, and it is defined as the work of 1 joule done in 1 second. Other units of power is 1 kilowatt. 1 kilowatt is 10 to the power 3 watt. 1 megawatt MW is 10 to the power 6 watt, and 1 gigawatt GW is 10 to the power 9 watt. The CGS unit of power, there is no additional name to it like watt here. The watt unit is for power in SI system, but CGS equivalent does not have a special name. It is directly written as erg per second from work by time. Work, the CGS unit is erg, and time CGS unit is second, so it turns out to be erg per second. Now the relation between watt and erg per second can be found out quite easily. Let us do it. 1 watt is 1 joule per second, and in our previous lecture we saw that 1 joule is 10 to the power 7 erg, and 1 second is the same unit in both the units. Therefore 1 watt is 10 to the power 7 erg per second. This is the relation between the SI unit and the CGS unit of power. There is a special unit of power which is specially used in engineering, and that is called as a horsepower. It's not SI unit, it's not CGS unit, it's a special unit used in engineering backgrounds, and it is called a horsepower. 1 horsepower represented as HP. It is horsepower, and this is equivalent to 746 watt. So when someone says engine has a power rating of 1 horsepower, that would mean that it has a power rating of 746 watt, or 0.746 kilowatt. Now this is about the units of power. We saw the definition of power. We understood the difference between power and work, that power is basically the rate of doing work. We saw the different units. We saw the relation between the CGS unit and the SI unit of power. Now let us see what energy is. Energy is the ability of a body to do work. Energy is ability of a body to do work. What does it mean? It means that energy is the stored quantity which is necessary for a body to do work. Basically, when a body does work, it spends its energy. When work is done on the body, the energy of the body increases. So energy is a manifestation of the body's ability to work. Work done on body decreases its energy, and work done on the body increases its energy, increases its energy, and work done by the body, that is the body is spending work done by the body decreases its energy. This is the preliminary idea behind energy. So basically, energy and work are parallel concepts. And since they are parallel concepts, the units of energy and work are also parallel. And energy is a scalar quantity. I'll mention it here. It is a scalar quantity. Energy is a scalar quantity. And now if we want to see the units of energy, it will be the same as the units of work. Same as work. So the SI unit will be joules, joule represented by a J, and the CGS unit is erg, and similar to work there will be other higher units, that is kilojoule, megajoule, gigajoule, and the relation between the SI and the CGS unit is that 1 joule is 10 to the power 7 erg. This we have already discussed while discussing the units of work. There are several additional units which are specific to energy. Why is it so? Because they are more appropriate for energy than they are for discussing work. What do I mean? Suppose the energy you spend in your household in the form of electrical energy. The unit for the amount of electrical energy spent, the bill that you get at the end of the month, is given in terms of kilowatt hour. Now let us discuss first watt hour. What is a watt hour? Then we will go to kilowatt hour. Watt hour. From the name, it might appear that there is a watt, so it should be related with power, but actually it is not a unit of power, rather it is a unit of energy. Let us see how. This is for power, this comes from power, and this is time, and we know that work, power is work by time, therefore work can be expressed as power into time. That is exactly what is done here, power into time. So this represents work, and how much work in SI unit is equivalent to 1 watt hour? Let us calculate that. 1 watt hour is equal to a power of 1 watt used up for 1 hour. Now 1 hour is not the SI unit of time. We have to convert 1 hour into the SI unit of time. Then we can write 1 watt is the SI unit, so no need to change that. But 1 hour is 60 minutes, and each minute has 60 seconds. So this is now in seconds, which implies that 1 watt hour is 3600 watt into second, and we know that watt into second is joule. So we got the SI unit. 1 watt hour is equal to 3600 joule. Now the higher unit, as I said, which is used for the electricity bills, is not watt hour, rather it is 1 kilowatt hour. And we already know what 1 watt hour is. So 1 kilowatt hour will be 1 kilo times a watt hour. That means 10 to the power 3 times 3600 joule. That will turn out to be 3.6 into 10 to the power 6 joules. And this can alternatively written as 3.6 megajoule, because 10 to the power 6 joule is a megajoule, so it is 3.6 megajoule. Now we have seen the SI unit of energy, we have seen the CGS unit, and we have seen the unit watt hour and kilowatt hour, which are specific for the electric energy that we spend in house. It can be used in a question to show you the amount of energy consumed by the process or released by the process, but normally it is used as a unit for electrical energy. Now we will discuss two more units of energy. One is called a calorie. A calorie, let me do it here. You might have heard the word calorie. 1 calorie is defined as the amount of energy that is required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. It is amount of energy required to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. The point to be noted is that the rise should be from 14.5 degrees Celsius to 15.5 degrees Celsius, because with the variation of temperature, the amount of energy required to raise the temperature by 1 degree Celsius also changes. So calorie is defined for the 1 degree rise from 14.5 to 15.5 degrees Celsius for 1 gram of water. Now, what is the equivalent of 1 calorie in SI unit? We know the definition, but we don't know the SI equivalent, that is how many joules are 1 calorie. So let us see how much that is. 1 calorie is basically 1 calorie is 4.184 joule. Some places you might find it written as 4.18 joule, or some places it might even say 4.186 joule, but you can approximately use 4.18 or 4.184 joule. So this is the SI equivalent of 1 calorie. We have seen the definition, we have seen the SI equivalent. Now we will go to our last unit that we need to discuss in today's lecture, that is 1 electron volt. 1 electron volt is represented by 1 eV. You can write the complete 1 electron volt. This is defined as the energy gained by an electron, energy gained by an electron when it is accelerated through a potential of 1 volt. When accelerated through 1 volt potential. This is the definition, that 1 electron volt is equivalent to the amount of energy that an electron gains when it is accelerated through 1 volt potential difference. Now what is the SI equivalent of this? The SI equivalent of 1 electron volt can be found out to be 1 electron volt is equal to the charge of electron into the voltage Q into V. That is the energy relation between charge voltage and the amount of energy. So the charge of electron we know is 1.6 into 10 to the power 9 minus 19, and voltage here is given as this many coulombs and the voltage is 1 volt. Coulomb and volt are the SI units, so the resultant 1.6 into 10 to the power minus 19 is the SI unit equivalent work. That is, it should be 1.6 into 10 to the power minus 19 joules. Therefore 1 electron volt is this many joules. Okay, now we have seen several units. We saw the SI unit, the electrical unit, the calorie, which is mainly used when we will study about heat, and electron volt, which is mainly used when we discuss about electrons, when we discuss about very small amounts of energy created due to potential differences. This is the theory of energy. Now let us do an example and understand better the whole thing. This is a simple energy equivalence question which asks us to find how many electron volts are there in 1 calorie of energy. So basically we need to convert 1 calorie energy to the number of electron volts. Now as we just read, 1 calorie is equal to 4.184 joules of energy, and 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule of energy. So we need to find out how many times this is equal to this. That will give us how many electron volts are there in 1 calorie of energy. Let us try to do it. Basically we need to find 4.184 is equal to how many electron volts. So let us assume that there are x electron volts. So x electron volts, and each electron volt is 1.6 into 10 to the power minus 19 joule. So this side is now in joule and this side is also in joule. This will give us x is equal to 4.184 divided by 1.6 into 10 to the power minus 19. This is in denominator. I can take this into numerator and write it as 10 to the power 19 into 4.184 divided by 1.6. This will imply x is equal to, let's use a calculator to solve this. So 4.184 divided by 1.6, and that is equal to 2.615. So x turns out to be 2.6615 into 10 to the power 19. Now what was x that we had assumed? X was the number of electron volts. So we get the answer as 2.615 into 10 to the power 19 electron volt is equivalent to 1 calorie energy. This was a simple unit conversion, finding the equivalence doing unit conversion. But in the next lecture we'll actually see the numericals, which will have components of energy, components of work, and components of power. We'll see detailed numericals in our next lecture. So till the next lecture, have a great day. Goodbye.